Okay. Well, good afternoon. Welcome to the second blind simulation competition that we are organizing in the scope of the activities of the Fibre WP241 related to the assessment of the predictive performance of FEM-based models for simulating the behavior of fiber reinforced concrete structures. So now we are initializing the second test, the same. So we are testing twins shallow beams. So, well, as you see here, and as I explained in our competition, so this is a continuous shallow beam where we have two supports in the extremity and one support in intermediate in the origin region. And well, we have a reinforcement, conventional reinforcement in the top part of the origin region, and we have a flexural, conventional flexural reinforcement in the bottom in the both sagging regions. So at some time we have fiber reinforced concretes, and so the idea is to verify the influence of fiber reinforced concretes for continuous beams. So this is we have relatively scarce material in this domain, and well, we expect to obtain with this test very important information for verifying the influence of fibers, not only for service limit states, but also to ultimate limit states, but mainly for service limit states. This is why we are using DIC to measure the crack width and the crack spacing here in the sagging region, so in intermediate supports, as well as in the sagging region, in one of the sagging region. So the test is already started, and so this is, as you see here, so this is sponsored by Fibre, Casais, Univital, Civitest, ArcelorMittal companies or organizations, as well as by our laboratory and our research center, IZZ. So we see here the one of the loads in the sagging region, so, and the other loads, and we have LVDTs that are measuring in the other face of the beam. We are measuring the deflection. We have installed in the top part strain gauge to measure the compressive strain in fiber reinforced concretes, so in both origin regions. And we have in the bottom we have also installed strain gauge in the conventional reinforcements. So we have 4 bars of 5 millimeter in the bottom, as well as 4 bars of 5 millimeters in the top. So it's a relatively small content of reinforcement. Well, now I will ask to our technicians what is the load, because we cannot see at the same time the relationship between the force and deflection. So this means that I will ask to our technician what is the deflection as well as the force, in order that you have an idea of the installed force. Mr. Matos, have we already started? Not yet. Not yet. No? So we are waiting for starting. So, well, what I can indicate. So, in fact, in the first shallow beam that were tested Wednesday, we are now post-processing the data, and this information will be sent or will be available together with the one that we are obtaining now in next days. Then this post-processing data will be carried out, executed by a researcher that we have in this project, Marcilio, and also with the collaboration of Beatriz Sanz, that is the deputy of our group. Matus? Not yet? Now it started. Okay, so we are starting. Okay, so I will try to show you in a more comprehensive way what is happening, because in last time the test was too static, so the cameras were always fixed, and then it was not very friendly to see, or did not provide good information for the attendance. So now I'm trying to comment what will happen. As you can imagine, so in the arching region, that is the region that I'm pointing out now, so we expect to have the first cracks. Okay. So this is the top. Up to now, we have not yet any cracks. Okay. So I suppose that you see now the top surface of the arching region. And as I explained, we expect to have the first cracks appear in this zone. We have here the DIC. Now we have 13 kilonewtons. And what is the average deflection, Marcus?
Deflection is about
4 millimeter of the average deflection in the session region. Yes, in session region, where we have the loads applied. I suppose up to now we have not yet any visible crack.
5 millimeters,
16 kilonewtons
5 millimeters.
and 5 millimeters of deflection. And up to now, no visible crack. But so we have already cracks in positive bending moment. It is more simple to see because the lateral faces are painted by white color, and so we have cracks in the bottom, obviously, and in the lateral face. So we can see the cracks that are progressing in the lateral, and obviously we expect to have we have already cracks in the top. It's not yet visible because it's so we have already a crack here. So do you see? Cracks just in the middle. So we expect that the fibers that are crossing this crack contains or restrain the propagation of this crack, and other cracks will be formed. And consequently, the stress label in the conventional reinforcement will be also decreased or will be smaller if we compare to plain concrete or reinforcement plain concrete. Yes, but 9 millimeters of deflection and 21. 20 kilonewtons and 9 millimeters of. We see another crack here. Do you see? So in the lateral face, it is painted in order to measure the crack width and the depth of the neutral axis. This, which will also very valuable information for the assessment of the predictive performance of the models. So it is not simple to see by naked eyes, but with the camera, with the photos that we are taking, and after post-processing, we are sure that this information will be very useful, very visible and useful. So we see here the crack. So one crack here, The other crack,
In the lower is just one. The lower. 24.
so you are, okay. So the load that we are indicating is only one load in one session region. So this means that the total load is the double. So for instance, Matos, what we have now in terms of total load? So we have 42 kilonewtons and the average deflection is? Huh? 14 millimeter. So we have 14 millimeter deflection and 42 kilonewtons of total load, total applied load. So it is, as we can see, so we have already a very large deflection. Okay, so okay, and now looking for the cracks. So look for a very large number of cracks. This is what we expect in fiber reinforced concrete. So because well, the influence of the fibers crossing the cracks, so limit the crack propagation, and this contributes to the formation of another cracks, and consequently to decrease the average crack spacing. So we expect also with this information to assess the reliability of the models that we have nowadays for estimating the crack spacing. So now we have 44 kilonewtons of total force and 21 millimeter of average deflection in the session region. So do you see? So we have the cracks in the top. It is quite visible, the formation of a macro crack just in the middle of the support. Now the load is almost constant at 45. So the load is almost constant at 45 kilonewtons. So in the previous one, the load was close to 40 kilonewtons, because I have already analyze the load versus mid deflection, and the maximum load was about 40 kilonewtons. Now we have 45 kilonewtons. So in fact we have the localization of the crack. So we have now like a pseudo no, is a real plastic hinge in the arching region, and now so it is progressing. So we have a certain momentary distribution, and so the stresses are moving to the session regions up to the localization of the next plastic hinge. So we expect also to have a relatively small strains in the conventional reinforcement due to the contribution of steel fibers, but we will see this in the results. So this is my expectation. So a very large deflection up to now. So Matos, what is deflection? Deflection. 30 millimeter of average deflection in the session regions where the load is applied, and the load maintains constant, no? Is almost constant. Okay. Okay, we are realizing from the data that we have a larger loads in the right session region than in the left, because as you can imagine, isotropy is an ideal situation that never happened, mainly in reinforced concrete and concrete structures. But the difference is about 4 kilonewtons. So the difference between the load applied in the right and in the left is now about 4 kilonewtons. So we can see that the depth of the neutral axis is very deep, or is very high. So well, in the bottom, as you see, in the bottom we have a strain gauge to measure the compressive strain, and consequently to verify what is the strain level that is attained in the bottom. Okay. The load is starting decreasing a little bit. What is the load? Sorry? 44. So the load is decreasing, but it's a very small decrease. 34 millimeter of deflection, 44 millimeter of average deflection in the session region, and 44 kilonewtons. So it is in a plateau, more or less in a plateau. Matos, do you have the possibility to know what is the strain? No. Okay. So it is another computer. No. 3 por mil. Okay. So the strain, the maximum strain that we have now is about 3 per mile. 3 per mile of the strain. Okay. So I suppose now at this moment the crack propagation is in a stabilized situation. So now what happened is that the one main crack is formed, so the damage is localized. Okay, thank you, Marcilio. Is localized in this crack, and consequently, well, since the strain gauges are in this section, so we can have the possibility that some of them enter in, start decreasing, because the crack start localized, and consequently we can have this situation. So the strains can start decreasing because the strains are now a little bit far away from the main crack, the failure crack. So okay, so we see another second crack, but is 43 millimeter of deflection. And the load, please?
No, 43 the load.
43 the load, so the load continues to decrease a little bit. And the deflection? 41. And 41 millimeter of average deflection. So we will stop the test at 50 millimeter. So we see relatively large deflection. And look here. So the main crack in this session region. So it's certain inclination. because we see in the bottom, so the crack is not totally orthogonal, to the axis of the elements, and this is why we have this inclination that we are observing in the lateral face. Now, in reality, the continuous beam is working like two simple support beams with a resisting bending moment in the origin region equal to the plastic resisting bending moment. Okay, so obviously plastic, but considering the contribution of the fibers. We have only 50 seconds to end, so we are almost closing the end of the test. And well, as I indicate to you, we will start post-processing the data in the next days. And well, as soon as we have this information, we will send to, or we will turn this information available for everybody, mainly obviously for those that enter in this competition. Okay, so it ends the test, so many thanks, and well, thank you very much to be participating in this, or to attend this competition, and also to attend this test. I hope that you enjoyed. And well, in the scope of this project, we are still planning to have another 2 blind simulation competitions. Next one will be for slabs submitted to punching, so to assess the influence of fiber reinforcement for punching strengthening, for punching resistance, and also for torsion. So this will be the last one blind simulation competition test. So many thanks. Okay, thank you very much. Bye-bye.